Hi. Now we're going to do 2 units on something I'm calling rate distortion autoencoders. And then we'll move on in the next section to variational autoencoders. So let's first review where we are. So we're interested in our standard cross-entropy loss for training neural networks, but we're interested in the case where Y, we're either trying to predict Y by density estimation from a population or some conditional Y. We're interested in the case where Y is a continuous structured object. And because differential entropy is somewhat problematic, and differential cross entropy is also similarly problematic, it can be arbitrarily negative, and we're minimizing. We need to be quite careful as we approach this problem. GANs avoid this problem, as I said in the last unit, by replacing the cross entropy with an adversarial loss. These rate distortion autoencoders and variational autoencoders are going to come closer to using the cross entropy directly. And I'm going to start with something that everybody's familiar with, and that's image compression. So you all know you take a picture, it's a very high resolution photograph, you want to send it in a message, you compress it, it's a smaller file, you decompress it at the other end, and it's lost something. The resolution's a little lower, or maybe there's some artifact, but you have this compression and reconstruction loss trade-off, right? The smaller you make the compression, the less accurate the reconstructed image is. So how compressed it is called the rate, how many bits it takes to transmit the object, and how well it reconstructs is measured in distortion. How distorted is the reconstruction relative to the original? And so what we're going to talk about is image compression. But I want to talk about it at a quite abstract level. So we just have some continuous structured Y, and we're going to convert it to a bit string, which is the compression of Y. Now, on a real computer, of course, all images are finite length bit strings, but it's natural to think of the original image as a continuous space and to think that we're compressing it to a discrete space. That's just going to be convenient. So this doesn't have to be a bit string. We're going to take this continuous image and we're going to compress it to a discrete set of possible values. And then we're going to take this discrete possible set of values, could be a bit string, but not necessarily, and we're going to decompress it into an image. And then we're going to look at the distortion between what we get back when we reconstruct it and the original image. And there's a trade-off between how many bits we need to represent the compressed form. And in a general setting, we've got this equivalence between log probability and bit length. And Shannon's source coding theorem says that that can be realized in principle. So I'm going to use this negative log probability, I'm using a discrete probability here for a discrete object that's computed from Y. So this is a legitimate cross entropy, no issues of differential cross entropy here. And then there's going to be a distortion. How distorted is it? And we're going to use something like L2 or L1 distortion measures, or at least that's what I'm going to talk about. And so this trade-off sort of avoids the problem with differential entropy, especially if we just think of this as a squared error. So let's talk about that squared error for a moment. So what people often do is sort of the oldest and most standard measure of distortion is to look over all the pixels. We'll assume these are the same dimensions. You look over all the pixels and you take the difference between those pixel values and square it and add that up over all the pixels. And then you can take a square root of that to make it in the same units as the pixels. And that's called root mean error, RMS, root mean square, or root mean error. So it's common to take this distortion measure. If I think of these images as vectors, you just take the norm squared of the vector. And I'm multiplying by some weight here, so it doesn't really matter whether I divide by the number of pixels or not. Now, I can define a Gaussian probability distribution if I assume that Y what I'm seeing is some true image plus Gaussian noise, then this is measuring, this can be interpreted as a log probability of y given y hat. And if I do that, I can actually, it's possible to interpret this squared error as a log probability. But that involves, it's not a log probability, it's a log density. And log density makes me uncomfortable because it can be arbitrarily negative. So I'm more comfortable just thinking of this as a square distortion. We can also use an L1 distortion. This L1, you take the two vectors, the images viewed as vectors, as sets of numbers at every position, and you sum over all the pixels the absolute value of the difference, and that's an L1 distortion. We saw this when we did GANs. Again, it's possible to interpret that as a negative log density, but that makes me uncomfortable. I'm more comfortable just talking about the distortion as distortion. Okay, the rest of this unit is going to be based on a paper that appeared at iClear in 2017. There's nothing super special about this paper except that it's demonstrating this principle of a rate distortion autoencoder that's taking an image to a discrete representation. It's all about image compression. So we take an image, we produce a discrete representation. This discrete representation in this paper is just a tensor whose elements are integers. So they're going to make it very compact. And then you take this tensor whose elements are integers and you reconstruct an image and you look at the loss, distortion between the reconstruction and the original. And this is just some random picture of a network. So we take an image that we want to compress. We apply a deep neural network to it. We take some particular layer in that. That layer is going to have spatial dimensions and feature dimensions, neuron dimensions. And we're going to round. We're going to take that tensor and we're going to round all of its entries. So that tensor has spatial dimensions and neuron dimensions. For each entry in that tensor, I'm going to round it to the nearest integer. Very brute force. So the whole trick here is going to be to get this to be a good tensor for this rounding. Now, if I'm going from a continuous object to a discrete object, the choice of the discrete object is not a differentiable step, right? If I round an integer, I can't, the derivative of that rounded value is 0 as I make little changes to the thing I rounded. So it's not differentiable. So in this paper, they use an approximation where they approximate rounding by adding noise between -0.5 and 0.5. So when you round, it either goes up by as much as 0.5 or down by as much as 0.5 to the nearest integer. But instead of rounding, you're just going to take the continuous value and add random noise that models rounding. Okay, and you're going to use this at train time. So at train time, this becomes differentiable. This is just the expectation over taking a training point and randomly drawing noise uniformly from -0.5 to 0.5 at each pixel. So epsilon is a vector here. This is at each pixel. You take the values in the tensor that you got out of your neural network and you add the noise to model rounding. And then you measure the distortion where you include the noise when you reconstruct this image. And this is a density now, right? Because it has to be differentiable. So this is a density that's also a real number computed from this and under these parameters. Oh, I should say, in GANs, I always distinguish the generator from the discriminator, and I used phi and psi. I'm going to just start using always phi for all the different parts because these are all cooperative. And you can just think of phi as having all the parameters of all of the parts. And that lets the various parts share parameters. So you shouldn't be confused by the fact that I've used the same parameter set in various ways. I'm even including it in the decoding. This whole system has one big system of parameters that I'm calling phi. Okay, and I'm gonna, this is telling me the probability of, the probability density of this value. But in this paper, they parameterize this probability density such that the probability density at a real number can be interpreted as a discrete probability of the rounding. So it's parameterized in such a way that this density is going to be roughly the same as the discrete probability of the rounding under this stochastic process of running the network and then rounding. Now at test time, we're actually going to use rounding. So this is viewed in this paper as a trick to make the rounding approximate the rounding by a differentiable function so that we can actually optimize the rounding. And they show that this approximation is good, is accurate. So what this is looking at is the difference between the differential entropy and the discrete entropy. It's the difference between negative log probability of this and negative log probability of this, right? So they're saying that this equality is going to hold, and this is empirical now. Now, what this axis corresponds to different values of the trade-off parameter. So the entropy is going to be, if we don't care about the distortion, we can make the entropy very low. If we care a lot about the distortion, the entropy is going to be higher. We're going to need more information. So this is like the number of bits it's in bits per pixel. So this says if I take an image and I run it through my network, and then I either round it or I add noise. And so I get a value for rounding, the discrete entropy, and I get a value for the noise version. And those two are very much the same across this whole space of lambda. So the model is good. And the same thing happens with distortion. I can take the image and I can round it, or I can add noise. And then when I go look at the distortion is going to be the same on average, whether I added noise or rounded. Okay, so they're using a deep network to do image compression. This is JPEG. This is a quite old image compression algorithm. So we're gonna see, this is JPEG. This is JPEG 2000, same image. JPEG 2000 is a stronger image compression algorithm. This is deep compression at this is even a smaller number of bits than the other two images. So it's showing that the deep network does stronger compression. Okay, so I'm just using this image compression system as an initial departure point that I think we can all understand, and I'm going to move gradually into. I'm eventually going to end up with variational autoencoders. But we're going to do something called a different version noise. We're going to do a different version of rate distortion autocompression autoencoders in the next unit. Thank you.